Paul has been a graduate of the University of Manchester, both undergraduate and PhD, where he worked in his thesis already on the parallel distributed databases, when I guess they weren't such a big deal as they are nowadays. He then went and worked in industry for a company called ICL, which at that time was bigger than Microsoft, but now it's been absorbed by other companies, and distributed further implemented further the distributed computing capabilities in that company, and then moved back to academia at the University of Newcastle. His research interests, not surprisingly, are in distributed and cloud computing, and he has a very strong industrial focus as well, so that he's one of the leaders of the Digital Economy Initiative of the Research Councils. Thank you, Paul.
Okay, thanks, Gavin. So it's a pleasure to be here, and what I want to talk to you about this afternoon is one of the main problems facing society today, which is social exclusion. And if you ask a sociologist, and we've got a few in our project, if you ask them to define social exclusion, they'll come up with something like this: the result of related factors that prevent individuals or groups from participating fully in the economic, social and political life of society. And that sounds like quite a dry definition, perhaps a bit academic, but actually this is a problem which affects large numbers of people. In Britain alone, it's estimated to affect about 10 million people, about a sixth of the population. And this includes older people who are perhaps struggling with ill health or isolation, people with disabilities, and also younger people on the margins of society. And at a conference like this one, where we're all interested in technology, you people here, PhD students, are inventing the technologies of tomorrow, it's worth thinking about what effect technology's had on people who are socially excluded. And in general, experts believe that what we're actually doing as a community is making things worse. And the reason for that is that as we become a more digitally focused society, if you can imagine, if you aren't able to access digital technologies, if perhaps you have a disability that prevents you from making full use of them, if you just don't have the skills to make use of them, then you're really at a disadvantage compared to the rest of society. And so what experts think is that the onward march of digital technologies will probably mean that people who are in this category will fall further and further behind the rest of society. And reasons for that are that if you aren't comfortable or able to use digital technologies, then you won't be able to get jobs which require even basic computing skills. If you can't use digital technologies, then you won't be able to take advantage of those services that are provided by governments, particularly nowadays when they've got this digital first agenda, because it reduces the cost for the government but makes it difficult for people to access healthcare, financial advice and so on if you can't use computer technologies. And the real catch-22, I think, is that one of the great things about the internet these days is all the wealth of learning resources that are available. And so if you like, the PhD students I know nowadays, if you want to find out anything about anything, be it to do with the research you're doing or work or anything to do with the rest of your life, then the natural thing to do is to go on the web, and there's all of these resources available to help you learn about it. So people who can't do that are in this terrible catch-22 situation that they really need access to resources to improve their skills, but they don't actually have the skills or the ability to get access to those resources. So as I say, a lot of experts see this very dystopian future in which people who are excluded grow further and further away from the rest of society because of the forward march of digital technologies. And so it's worth asking the question, I think, does it have to be like this? Or is there an alternative future which we could create? So about 3 years ago, a group of us at Dundee University, Newcastle University, started to get together to talk about whether we could actually explore how to use digital technologies to help people who are socially excluded. And our view, based on a lot of years of work at both universities in the past, was that, well, digital technologies have the potential to really make a difference to people, but only if more research is actually put into understanding how to apply those technologies, how to realise that potential to actually help people who are socially excluded. So this is the side project, Social Inclusion through the Digital Economy. We're about halfway through the project. As I say, it involves Newcastle and Dundee. I'm delighted to say there's some people here from Dundee University who are working on the project, so if you give me any really difficult questions, I've got people I can pass those on to. And what I want to do in the rest of the talk is two things. So I'll talk about some of the work we're doing in the project, about how digital technologies can help people who are excluded, but I'll also use this as a starting point to dive into some of the underlying IT, some of the underlying computing research which underpins what we do. And a lot of this is in the area of cloud computing. So I want to talk about cloud computing and how that actually helps us to achieve our goals. So the way the project is organised is on this two-dimensional matrix. So along the top you've got activities, which is where we do things in particular areas to explore whether technologies can help people who are socially excluded. And the point I'll make first of all is down the left-hand side, these perspectives. Then we're very certain that technology alone can't help to solve these problems. Sociologists call this technological determinism, the idea that you can throw technology at a problem and completely solve it. And we're certain that's not true. So we've built a multidisciplinary team, so we have sociologists. So they understand what it means to be excluded, how people become excluded, and if we make interventions with technology, then they can measure the effect of the intervention. We also do a lot of work with users. So we built up a pool of 3,000 users, drawn largely from excluded groups, who we use at all stages of our research. So this includes the very early stages, where we're thinking about which areas to focus on, right through to testing the solutions that we come up with. We also have some business experts in the project, and the reason for that is that a typical research project, what you usually do is you produce some prototypes and you evaluate them and you write some papers and then you move on. And there's quite a gap between that and actually getting technology out there at scale in order to really change people's lives, particularly if in order to do that you're dealing with people in the hundreds of thousands or the millions. And so what we have are business experts who are looking into how you actually take these technologies and get them out there at scale in order to make a difference to people's lives. We also have designers in the project. So, of course, design is a really important issue these days. We've all seen with the onward march of Apple how design can be very important. But designing systems which can make a difference to people who perhaps have disabilities or particular sorts of impairments or aren't typical users of digital technologies, it's really important to address these issues if we are to have the technologies that we produce widely adopted. So if I'll give an overview of some of these areas. So this is the first area. This is based in Dundee, led by Professor Vicky Hansen, and this is looking at the area of accessibility. So when you think of accessibility, you're probably thinking of things like making sure that if you're designing a web page that the font size is big enough so people with some sort of visual impairment can still read it, perhaps worrying about the colours for people who are colourblind. And there's a lot of expertise in those areas within the project, but we're also looking at other areas. And I've shown this picture here because it illustrates that digital technology are useful not just to actually build new things, make interventions and try to change people's lives, but as a first step just to try and understand people and their behaviour. So this is an example of you can see a lady looking at a web page, and what there is at the bottom of the screen there is a device called an eye tracker. So eye trackers look to see where people are focused. We'll see several uses of these through the rest of the talk. So this can show you where somebody's looking on a web page. And what's interesting about this is that if you ask older people, then if you ask them, why would you trust a web page? So trust is really important for getting particularly older people on the web. They're not like younger people like yourselves in general. Younger people are much more amenable to putting information onto the web through Facebook, Twitter, or whatever. Older people are very nervous. They're worried about being scammed and ripped off if they do that. So if you just ask them what makes them trust a page, they will say something like, well, It's to do with the brand. So if I'm looking at health information, then I'm likely to believe a page which has been produced by the NHS. If I'm looking at financial information, I'm more likely to believe a page that's from a bank that I know of, Royal Bank of Scotland, Lloyds, or so on. If I'm looking at information related to some government service, then I'll check the brand and make sure it's actually been produced by the government. And that seems a reasonable approach, and I think we'd all agree that that's a good starting point. But what you can do with the eye tracker is you can test that out. And actually, if you test it out, what you discover is that, in general, older people don't look at the brand. So there's a real difference between what people say and what you can actually discover by using technology to understand what they actually do in practice. And we keep seeing this, the difference between what people say, the information you get through qualitative methods, and the information you get through more qualitative means like this. And it turns out that, in general, what older people do is they go off how professional the page looks. So if it was a typical Nigerian scam type email with bad English and badly laid out, poor grammar, then they probably wouldn't fall for that. But if it was just professionally produced, nice photographs, well laid out, nice use of colours, then they're much more likely to trust that. So that's an example of using technology to really understand how people behave before we actually move in to try and do an intervention. Another area of this is mobility. So if you talk to older people, actually younger people as well, if you ask them what their number one concern is, then they say that it's mobility, being able to get around. And you can understand why that is, because if you want to go and visit friends and family, and you need somewhere to get there. You want to live successfully and healthily in your own home, you need to go out and shop. If you want to have fun, you need to go out to the cinema or the theatre, you need somewhere to get there. And there are generally two things that are important for mobility. One is public transport, which is particularly important in urban areas, such as Glasgow and Newcastle. And the other one is driving. So driving is important for people who live in rural areas. So we have some places near Newcastle, and I guess this isn't, you'll find this in Scotland as well, where there is a bus, but it's only every Tuesday afternoon, and if you want to come back, you've got to get the bus that returns on a Thursday morning. So people can't rely on public transport if they live in some rural areas. And so they rely on driving. And one of the effects you see is that as people get older, when they retire, they start to drive a little bit more. And you'd expect that because they've got more free time. But then, often quite suddenly, their driving tails off. And so we're interested in why that is and whether we can smooth it out and keep people driving safely for longer, keep people mobile for as long as possible. And so we've got this car, this instrumented car. So on modern cars, you can plug into the engine management system and you get all sorts of information. So every press of the pedal, every turn of the wheel, you can see from that system. And we also instrument the passenger. So we give them a bio belt, so they strap this on, and they can measure things like breathing rate and heart rate. And I'll just show you a little video to show you the information that we can collect from this. So if you look in the top left, you can see the view from a camera that's pointing out of the car. Top right shows a map of where they are. This is actually in Newcastle. And at the bottom, then this is the breathing rate, which is quite a good way to see how anxious people are. So at this time, the driver's getting more and more anxious. And you can probably tell why. He's getting to a busier part of Newcastle. There's parked cars on each side. He started to look around to see that there's a van on the left-hand side. A bit later, he'll start to look at pedestrians and worry about those as well. And the dots you can see, so this is another form of eye tracker. So you can actually get eye trackers now that are in the form of glasses, so you can get the driver to wear them. And this means you can see exactly where they're looking. So if you collect all of this information, there's quite a lot of things you can discover from it. So we've been doing tests with lots of older drivers for quite a while now. One of the things that you discover is that, again, the difference between what people say and what you find. So if you talk to older drivers, they'll tell you that they don't break the speed limit, that they're very careful drivers, very calm, and so they're always within whatever the limit is. And actually, using the engine management system and the information we can extract, you can see that they break the speed limit quite often, and they're shocked when you tell them this. And the reason seems to be, you can see this from the eye tracker, that when they get into places where there's a lot going on. So there's lots of information, pedestrians, parked cars, other traffic, perhaps lots of signs that they're having to take notice of. Then what happens is you can see that they don't actually look inside the car at the speedometer. They're always looking around and looking outside, so they forget and go over the speed limit. The other thing that you discover is that, and perhaps this isn't surprising, as you get older, your ability to judge speed and distance decreases. And so turning right against oncoming traffic is a real problem and a real cause of stress, and that causes the breathing rate to shoot up quite appreciably. And I'm considered an older person. I'm 50. I don't drive very much these days, but turning right against oncoming traffic is one of the most nerve-wracking things that you have to do, particularly when it's busy. You've got to judge, is the gap big enough, and put your foot down and go. And so one of the things that the people are thinking about, so we're still collecting this information so as to really understand these patterns of behaviour by older drivers. The next thing will be to start to look at interventions. And one thing we were wondering about was, what about sat-navs? So sat-navs are good in the sense that they personalise information for you, but the way in which they choose a route is based mainly on distance, so trying to minimise distance and also minimise time. And would it be better to think about sat-navs where you could also have a setting which reduce your anxiety levels? So try to avoid taking you into places where you had to turn right against oncoming traffic, for example. So you may go a little bit further in your route, but may avoid the sorts of situations that we're picking up here which cause anxiety to older people. It cause them to lose confidence and stop driving. So the next stage of the project, as I say, we're about halfway through the project. Once we've identified the main reasons why older drivers have problems, then we'll start to try interventions, including changes to sat-navs, to see whether we can help people drive safely for longer. Another area is connected home and community. So this is about trying to allow people to remain healthy and in their own homes for longer. And the first example I'll talk to you is about remaining healthy. There's lots of problems with particular diseases these days which are related to activity. So diseases like some sorts of diabetes, obesity, and also cardiovascular problems. The effects of these diseases can be reduced or delayed by exercise. But medics who we talk to say that it's a real problem, because what you want to do is to personalise the exercise regime for a patient. And in order to do that, you have to understand how much exercise they're getting at the moment and what sort of exercise it is. And so at the moment, all they can do is they can have a clinic, they can get the patient in, sit them down in their office and say to them, well, how much exercise do you do? And people might say, well, I do quite a lot of exercise. And so the doctor can say, well, tell me about it. And they might say, oh, well, I walk quite quickly and I do this for several hours a week. But it's very difficult from that to get a real accurate feel for how much people are exercising. So we were trying to think of ways in which technology could be used to give more accurate information to medics. So this is an example. So this is a watch with an accelerometer in it. So accelerometers measure acceleration usually in 3 different axes. And so there's one package in that watch. What happens is the patient comes to the clinic, a nurse gives the patient one of these watches, they're asked to wear it for a week. When they come back, then there's a USB connection and the data is sucked out of it and analysed, and a report presented to the doctor on how much activity the patient's had and what sort of activity it is and what sort of times of the day is the patient active and inactive. And I'll show you, just to show you how it works, I'll show you a video. The story behind this video is that I wanted to produce a movie, and so I talked to my researchers, who seemed to me to be about roughly your age, about whether they could think of anybody who was perhaps getting on a bit, perhaps somebody who needed a bit of help who we could use in the movie. So one name kept coming back again and again. So you can see, if I run this, you can see the chosen model walking down the stairs at Newcastle. Okay, and into one of our labs, into Culture Lab. And I'll just pause this if I can. There we are. Yeah, so you've got the same video at the top, but now at the bottom, you can see you've got 3 axes from the accelerometer. And in fact, the green one is down my arm as I walk like this. So you can see how many paces I take. Of course, you could do that with a pedometer, but you can see that you get more information because, for example, these peaks are bigger here than they are over here. And why is that? Well, that's because when I'm walking down the stairs, I'm actually doing more work than when I'm walking on the flat. So if I just run it on, you'll see that there's a transition there when I go onto the flat. So you don't just get information about how many steps I take, you get information about actually how much exercise I'm doing. And from the same accelerometry traces, we've got teams of people, some working in industry, some working in other universities, who feel they can extract different sorts of information from the same traces. So there's people who can extract information about sleep. So sleep is also important, and you can find out how much sleep people are getting and how deep it is from the standard characteristics of the accelerometer. You can also, one hope is that for older people, one problem that they often have towards the end of their life is they have a catastrophic fall because they become unstable. And the hope is, again, you can see instability in the way in which the patient's walking through the accelerometry, and so you could intervene before there was a problem. So that was a lightning overview of some of the project. There's a lot more on the website, but I want to dive in a bit now because I want to have a look at some of the computing science behind this. So what we want to do is we need to extract the information from the accelerometer of potentially millions of patients, do some analysis quickly because we want to do that analysis while the patient's still in the clinic before they see the doctor, so the doctor has the report in his hand or her hand before they talk to the patient. And we also might want to give some information from users, some information to encourage users perhaps to do more exercise or different sorts of exercise. So we wanted a scalable system which would do this. And in a side project, we have a cloud-first policy. So we're really interested in exploring cloud computing as a way to store and analyze data. So we don't buy servers, we always try to use clouds. And so the obvious thing to do here is to use clouds to store the data and also to do the analysis. And this takes advantage of the fact that in cloud computing you've got scalability in storage and scalability in processing. So even if suddenly the medics we work with are very ambitious, they'd like to sign up 1 million patients to use this system within the next year or so. If that happened, it wouldn't be a problem in that we could just grab more resources from the cloud and use that to store and analyze the data. So I'll talk a little about cloud computing in case you haven't come across it. So that's an example of a data center. This is actually a Microsoft data center. And cloud computing came about because companies like Microsoft, Yahoo, Google, Amazon needed to build large data centers to support their own activities. So in order to do search, as I'm sure you all know, you need a copy of all the pages on the web and you need to do some analysis of the linkages between them. So you need a lot of machines to do that on. And a data center like this, which is the latest generation, you've got about 100,000 machines within one of those facilities. And if I go to the next slide, which shows you what it's like inside there, so it's probably not like you imagine. You probably imagine racks and racks of machines. It would just take too long to build up all of these racks of machines within these facilities. So what they do is they outsource it to other companies. So you can see at the bottom there's this company, Rackable Systems, and what they do is they build server farms in shipping containers, and then they just truck them in to the cloud data center, and they're taken off the trailer, and then they're connected up to air conditioning and to power, and then the truck goes away. And they monitor how many machines have failed. They don't go into these containers, they just monitor how many machines have failed. They let them fail, how many disks have failed. When it gets below a particular level, then the truck comes back in and takes the container out and replaces it with another truck. And off-site, somebody then goes through and tries to replace the failed components in there. So all of the big computer companies are building these sorts of data centers. And a few years ago, they thought, probably this was in sort of 2004, 2005, they realized that actually, perhaps there was another way to earn revenue. And that was to allow external users to access the storage and analysis facilities which were in these data centers, but at a charge. So what they do, it's a pay-as-you-go type system. So you pay roughly 10p an hour for processing and about 10 pence a month for a gigabyte of data storage. And so it's really not the technology. The technology, if you were allowed to look in one of those shipping containers, you'd probably be quite disappointed because the computers in there are probably of lower performance than the computers under your desk at work. They're just very cheap machines. They don't put anything in them that you don't need, so they don't have graphics cards, for example, because obviously those are pointless. The idea is just to keep the cost and the power consumption down as much as possible. But the attraction of them is you can grab as many as you want, up to thousands, and you pay as you go. And you can get them just as you need them. You don't have a long-term contract. At the end of this talk, if you had a credit card, you could go and grab 1,000 nodes from Amazon or Microsoft and use them for a few hours and then give them up when you're finished with them and just pay for the time that you use them. And so this sounds great, that it sounds like it could be a revolution in IT, democratizing IT, making all of these processing, storage and power available to anybody, be it somebody starting up a company from the back bedroom or some lone researcher who doesn't have access to large computer facilities in their own university. But there are real problems, and what I want to talk about is two of the main problems that there are, and look at some of the ways we've been trying to address them. So this is the main problem. So when you go and use cloud computing, what you're actually getting for your money is very low level storage and compute power. So you're getting just about bare machines. You can do whatever you want. You can put whatever operating system on you want, whatever software you want. But the problem is that for most people, for most organizations, then building the sorts of applications that they want on clouds is just beyond them. And it's because if you look at the applications people need, think of the healthcare application with the accelerometers I've just talked about. What do you need? Well, you need scalability because you need to go potentially up to millions of patients. So you need to be able to grab servers as you need them, as the number of patients increases. You need reliability. It's no good if the system falls over between the patient presenting their watch to a nurse and the report being generated ready for the doctor. And you also need security because some of this information is perhaps medically sensitive information. So building scalable, reliable, secure applications is a real challenge. And so for that reason, the use of cloud computing has been restricted largely to people, I guess people like yourselves, who do have the skills in order to write those sorts of applications. And most of the people who potentially benefit aren't able to do so. So for the last few years, we've been trying to think about how to overcome this because we work with lots of researchers, besides one of our projects, but we work with about a dozen different types of research groups and trying to think about how to make it easier for them to exploit the cloud. And so what we've done is we sat down a few years ago and thought about what would cloud middleware look like. So if you're building if I set you off to build, let's say, a web-based system, you wouldn't start from an operating system and start to build a web server. You'd build it all on middleware. You might grab a JBoss web server, you might go and get a database from another company, and you'd start to build systems on top of that firm basis. Like somebody else has already done the legwork, somebody's done the difficult part, and you can build on top of that. So what would those services, those equivalent services, be like for clouds? And so the system that we come up with is this one called eSign Central. So at the bottom, you've got processing and storage, which you can grab from clouds. So the system's portable, so you can run it on Amazon, Azure, or private cloud. So you can put it on your own servers in your own organization. And then you can upload data, and you can annotate it with metadata if you wish. For example, in areas like biology, they have standard ways, standard XML formats for metadata so that people can find and interpret the information that's stored in the system. You can connect as a user, so you can do everything through a web browser, so you can connect as a user, and then you can connect to colleagues in a social networking type way. You can create groups, and that then allows you to decide on security. So anything that you put in there, all your data, you can keep to yourself, or you can share with other people or with groups of people. You can also upload services, so you write services in Java or Octave or R or some other languages, and automatically upload them to be executed in the cloud. And then you can create workflows. So workflows have been very popular in e-science as ways to choreograph the execution of applications from sets of services. So you can do all that. As I say, you can do it all through a web browser, and you also do it through an API. So you can hide all this behind some other application. So we built this, and we use it in quite a few systems. So here's the use of it for the accelerometry. So you can see here, this is some of the accelerometry data that's been uploaded into eScience Central. This is one of the workflows that we've created. We've got an HTML5 workflow editor, so you can create these by dragging and dropping services from the categories on the left. And as I said, there's an API, so this is actually a Windows program that the nurses run in the clinic, which then talks to eScience Central through the API. So when the patient arrives with a watch, the nurse plugs into a USB connection, puts an ID in for the patient, presses a button, and it gets uploaded into the system to be analysed. And then the doctors get a range of information that they want. This is one of the simplest forms where it just splits it up by day and tells them which periods of the day where the patient was most active and least active, and what value that was in terms of activity. There's some more sophisticated outputs as well. So for example, this is one from some of the researchers who are interested in activity levels across a whole population of patients and how you model that. So this is the blue line's the model that they built from the empirical data that they collected. And the system scales, so this is an example of a workflow that scales over 200 nodes. This happens to be on Azure, but it goes at about 90% efficiency across the 200 nodes. And for this particular application, the scientists who came to us, they had an application that they thought was going to take 5 years to run on the server that they were currently using. And we managed to get it down, with help from Microsoft, we managed to get it down to about 10 hours instead of 5 years. So this is running a big workflow with about 4.5 million service calls. So the reason for telling you about this is that as PhD students, one of the things that you're doing is working in different areas. And of course, one of the areas that is important in computing science is to try to identify particular patterns that occur many times in different applications, and to explore those computational patterns, and then to provide high quality, scalable, dependable, secure implementations of them. So this was our effort to identify patterns in the way in which we saw clouds being used and implement them once, so that then hopefully everybody else can have the benefit. But I wanted to move on to security, because actually one of the things that came to us when we were doing this was that we still had quite a major issue. And that was that if you look at the standard workflow that we were running, so we had this patient data from the accelerometers that we collected. It also identified the patient, and then you anonymized it effectively by getting rid of the patient data, and you just had the accelerometry data, which you then wanted to analyze. And this was where most of the scalable processing was required. And finally, in the end, you produce the results which end up in the reports which the doctors get, and which are then fed back to the patients. And the problem was that the medics had signed forms which said that the patient confidential data, this data here, which happened to have the accelerometry data with it, would not leave the university's servers. And that's not uncommon. There's a lot of restrictions on moving medical data out over the internet. So the idea of moving it out to Amazon or Microsoft Azure over the internet to somebody else's cloud to analyze it, that was completely out of the question. And so what we used to do for this and other examples was that we'd get the application scientists in, and over a coffee we'd talk to them about whether or not there was any confidential data, whether there were any problems with using public clouds. And if there were, then we'd say, well, it's okay, we'll grab some servers inside the university and we'll put eScience Central on that, and we'll use it as a private cloud, an internal cloud, and the data will never go out. Or if there wasn't a problem, if all the data could move out of the internet, we'd just run it on Azure or Amazon and take advantage of the scalability. But the real problem with this was that if we did this, then that would mean for this application, we could only run this within the university because of this data here. So all those millions of patients coming into the clinic, every time there was an increase in number of patients, we'd have to go out and buy more servers and find somewhere in the university to put them, until we'd end up with not as big as that Microsoft facility you saw, but quite a sizable machine room, which we didn't want. It seemed wasteful. It's hard to get capital in order to buy those sorts of servers. So wouldn't it be nice if we could do something different, which was that why can't we just keep this data inside the university and allow the anonymized data produced here to go out and go to Amazon and Azure to be analysed, where they have scalable capability. And so we used to do this by getting a clever person called Simon, a clever programmer, who would be able to take this workflow and split it into two workflows, run this bit on a version of eScience Channel within the university, and then this would send the data out to another version that was running on Amazon, where it would be further processed. And for this sort of workflow, that wasn't too bad. It didn't take too long, but I really worried about it. We worried because in a simple workflow like this, it's quite easy to see where the security issues are and how to address them. But some of the workflows we had, you saw that one with 4.5 million service calls in it when it was run. I wouldn't really fancy asking somebody to work out how that could be partitioned across a set of clouds and put the hand on the heart to say that we definitely conform to security requirements. A lot of these workflows are really complicated. So what we wanted to do is to try to come up with a way to do this automatically. So again, this is a reason I'm going down this particular path, is because I hope it's interesting, but also because I think it illustrates something else about computing, which is that what we try to do in computer science is to try to provide formalised ways of dealing with things which otherwise would have to be done in an ad hoc manner. And so we came up with a formal process for doing this, and it's in a paper, and I won't go through all of the stages in detail, but I'll just show you roughly how it works for the running example. So we started with an existing security framework, perhaps the one that's the most popular, most common one over the last 30, 40 years, which is called Bell-LaPadula. And the reason it's common was that it was widely used by the American military. It was based on the idea that you had people in the military who had ranks. So they could be privates, corporals, majors, sergeants, generals, chief of the defence staff. And so these ranks basically give you their security level. And then you had documents which had classification, which could be unclassified, could be private, could be highly secret, could be top secret. So again, you've got a set of levels of security. And all that Bell-LaPadula did was they introduced two rules. So one of them was that nobody in the army can read a document which is at a higher security level than they are. So if you're a private in the army, you can't read things that are top secret because that's a higher security level than your rank. But if you're a general, you would be able to do that. And then the other one, which is a little counterintuitive, is that nobody could write a document out at a lower level than their security level. So this is the no write down rule. Okay, so you can read things that are a higher level, you read things that are a lower level, and you can write things out that are at a higher level, but you can't write things out that are at a lower level. And the reason is they didn't want leakage of information. They didn't want a general to read something which was confidential and write it out as being in the public domain. And this causes problems, of course, because if you just follow that rigidly, all information goes up and up and up in levels, and how do you ever produce, for example, a summary for the local newspaper or a paper for a publication? So they have this other rule which says that actually the member of the military, although they might have a rank which effectively gives them their highest level of security, they can, for a particular application, choose to work at a lower level. So they split up this coverage, which was the highest level, from the location, which was the level they were currently working at. And so what we did was we mapped that onto our workflows. So services, we thought, are like the members of the military. So services that can process top secret information because you trust them, you don't think they're going to leak information out. They're like the generals or the chief of the defence staff. Some service that you've just downloaded over the internet that you have no idea about, that's like a private in the army. You don't really know what they're doing, and you don't really trust them very much. And similarly with data, so we made the analogy between data and documents. So something like the medical data was the equivalent of top secret data in Bell Lapidula. So we did that, and then then what you do is, for any workflow, you go through and you assign security levels. So it works with any integers, but for this I'm going to just use 0 and 1 for simplicity. So 1 is top secret, 0 is very low level of security. So 1 is assigned to this patient data, but the anonymized data is at level 0, and so are the results. Similarly for the services, then the anonymized service is at clearance 1, so it's allowed to read top secret data, this medical data, but it's also in this case operating at level 0, so it can write out the anonymized data at the low security level. So you do that, and then you assign a security level to the cloud you're working in. So as far as the medics are concerned, their private cloud within the university is at the top level of security, whereas Amazon and Azure, these public clouds, are at a low level of security. And then you add one more rule, which is an obvious one, which is that no service or data can be stored or deployed on a cloud which is at a lower security level than it is. So if you don't trust a cloud, you can't put high security data onto that cloud. I think that's pretty intuitive as a rule. And basically that's largely it. So if you take that 5-block workflow and you work out all of the different ways in which you can map that onto 2 clouds, then there's 16 ways to do it. Okay, so why is that? Well, you've got 2 clouds, you've got 5 blocks, so 2 to the 5, 32 is all the possibilities, but the top security block, the medical block, can only go on the high security clouds. That reduces it by a factor of 2 to 16. So there we are. So we've run this through the tool, and we found there's 16 options. So is that it? Could I send somebody out to implement any one of these and we'd be okay? Well, it turns out you can't. So there's one complexity, which is to do with the fact that if you've got a service which is reading data from another cloud, then there's no way it can do that without taking a local copy of that data. There must be a copy somewhere near the service, either just in an operating system buffer or in a file. And similarly, if you've got a service which is on cloud A, which is writing out data onto another cloud, then it must somehow take a copy locally so that that copy can then be transferred over the network. And so effectively what we had to do was to introduce some transforms into the workflow to take into account of this. So if you've got a service that's on the same cloud as the data that it produces, that's fine, you don't have to do anything. But if you've got a service that's producing data on another cloud, then you transform it so that service produces a local copy which is then transferred over to the remote cloud. You've got the analogous case up here where you've got a service consuming data on another cloud. So we have to go through all of our workflows and apply these transformations, which effectively changes the security lattice. And at the end of that, you end up with 6, which we were surprised about. So we started, remember, with 32 possibilities, and by having a methodology to deal with security, you reduce that first to 16 and eventually to only 6. Okay, so we could stop there, and that could be it. But actually, that would mean that somebody, a human, would have to work out which was the best of these 6 options to implement. And so we wanted to try to have a method for that as well. So what we do is we introduce the idea of a cost model. So we have a cost model which works out how much each of these options costs. Now I said that for cloud you pay as you go, and there's 3 costs. So the first one is to store data, and that's based on the size of the data and longevity. So every piece of data we've got in the system, you give the cost model an estimate of its size and how long it needs to be retained, and then you multiply it by the cost for that cloud of keeping some data per unit time. That's this E part of the equation. And then you add to that the CPU cost. So any service, you get an estimate for how long it takes to run, and you multiply that by the cost of CPU on that cloud. And then you've got transfer costs. So cloud providers charge you for transferring data in and out of the cloud. So you also add that into the system. And if you do that, you can then work out the cost of every deployment. So these are the estimates for this particular workflow of the sizes and the longevity of data, and also the CPU times. So that's what I fed into the model. Here's an example. So here's two clouds, C0 and C1. One's the low security cloud, the other the high security cloud. If the costs of those are exactly the same, then when we push that through the cost model, then the ordering of cost is, and I've shown in order of 1 means the lowest cost is the one on the right hand side. So why is that? Well, actually the costs of storing data and doing processing on each cloud are exactly the same. So the only difference in costs is where you incur a cost for transferring data from one cloud to another. So all that this is doing is saying that the only option where you don't transfer data at all, so you don't incur that cost, so that's the cheapest. Now that's not really realistic, because we want to use public clouds because they're scalable, and it works out cheaper to do scalable processing on them than it does to buy the servers and put them in your own machine room. So if we now differentiate between these two clouds, so the public cloud, let's say Amazon, costs half as much to store data and half as much to process data as your private cloud, you put that through the cost model, then this one comes out the best. And the reason is that what this one does is it does the minimum amount of work on the private cloud, which is more expensive. So it gets the initial data, it does the anonymization, and then it sends it out, transfers it out to the cheaper public cloud to do the data intensive analysis down here with this service, and then store the result. So the idea here is that we've gone from a system where we started with a clever programmer working out how to split up this workflow and programming it themselves directly, to a method which we hope is correct. In fact, we've had it formally proven now, so we hope there's no mistakes in the proof or in the implementation. But it seems to work, and that means with confidence and automatically we can generate the best option given a particular set of security requirements. And so now what we're doing is moving to this sort of model where you saw the workflow at the top. Instead of just directly deploying it on a cloud, what you do is you put it through a policy manager where you specify. So we moved on not just security requirements but also dependability requirements, and we're going into performance requirements next, and it works out how best to partition it across a set of clouds. Okay, I'm rapidly running out of time, so I'm going to go to the last slide. So I've tried to do two things. I've tried to show you examples of how the SIDE project is trying to realize the potential of digital technologies to help people who are socially excluded. And the other side of what I've done is to try to show you how cloud computing has potential, but there are issues. However, as computer scientists, we can try to address those issues and solve some of the problems to make it easier for people to produce scalable, reliable, dependable, secure systems built on clouds. And the final thing I hope is that one of the reasons I went through this was because the idea of this security model, it didn't come to us when we were just sitting around in coffee at work because it seemed like an interesting thing to pursue. I don't suppose we'd ever have thought that there was an issue there, that we might need to use federated clouds, and that we needed methodologies to do it, unless we had this challenge. And the challenge came from working with some medics who were trying to achieve something. In order to do that, they had a particular set of requirements. We had a system that we thought could help them, and we realized that actually our system couldn't do that it couldn't meet the challenge, and therefore more research was needed in order to address these problems. And so this is why I put this up as the third bullet, which I hope is the main thing you'll take away, which is that I'd encourage you all as students, but also in the rest of your careers, to, when you're working in particular areas of computing and computing research, to try to find interesting real-world problems that you can address, where you can work with clever, interesting people solving challenging real-world problems. And the reason for that is not just because, as we do work in the SIDE project, trying to address problems that people are excluded and finding it a rewarding thing to do. I think it's a good thing to do in general because it challenges your research. It gives you the impetus to go in and think of new problems and try to come up with solutions to them. And once you've done that, then you can feed those back through tools and hopefully everybody can benefit. Thank you.
Thank you for a very interesting seminar. Questions?
How do you establish this trust relationship? Or do you just know a priori that one cloud is trustful and another is not?
Yeah, so it's a socio-technical problem. If you talk to somewhere like Amazon or Google, they will tell you that they are certified to a particular level for their cloud. And if you read the small print, it's quite interesting because sometimes to get to a particular level seems to mean you need barbed wire and men with guns walking around outside the building to make sure it's physically secure. But, so that's one thing that you could use to determine how secure you believe something to be. But actually, largely, I think it's social. That the medics we work with, they sign forms to say that they will keep data within the university, and they do that because they believe that it's safer to do that rather than have it go out of the internet to a managed facility by Amazon or Microsoft. Now, that may or may not be true, and we can have you can have a long discussion about that, and certainly Microsoft and Amazon and Google would disagree with them. But once they've signed that piece of paper, and if that's their belief, then there's nothing you can do about that. So rather than address that problem, what we do is we just say, well, you give us your judgment on the security levels of the clouds that you're offering us to work with. And we just encode that as a security level 0 and 1 in this case and put that into the model. But we don't try to automatically work out what the security level is of a cloud.
Thank you. Thanks for an interesting talk. In terms of the cost models, sometimes prices change, don't they? Amazon have spot instances and price goes up and down. And do you include that notion of adaptivity in your cost modelling?
So if I could go back to this slide here, then so the first implementation is what I talked about. You see these blue lines, it was basically everything was coming down. So you specified the workflow, you specified the requirements. The tool, it's actually written in Haskell actually. I guess you had Phil Wadler, is it?
Yes.
He might have mentioned functional programming. So.
He did mention
okay. So that's written in Haskell. And it produces these partitions which are then deployed on eSign Central. Now, in the last 6 months, thanks to EPSRC, we've been working with a local company called Arjuna, and they have a dynamic policy manager. And so what happens then is you can take into account these green arrows coming back. And so if prices change, or if systems disappear, and there was an outage last week by one of the main cloud providers, for example, it does happen every now and again, then you can dynamically repetition based on the current state.
Question?
I was going to ask about the first part. So you have kind of older people that are struggling or kind of confused by normal tasks, and so now you're going to give them like complicated technology. How do they respond to being given like this stuff that maybe to them is almost like taking care of them or something? And do they find that very strange? Do they look at as a person or?
Yeah. So I think the idea is not to give them technology that they find complicated. So that's why you need to involve them at an early stage, and that's why design's important. So, for example, I didn't have a chance to show it, but we have this thing that's been worked on at Dundee Newcastle called an ambient kitchen, and that uses pervasive computing. And for people with dementia, that tries to help them to carry out basic tasks that they need in the kitchen. For example, just making a cup of coffee or cooking a simple meal. And the way that works is it just monitors what they are doing, and then it prompts them either audibly or visually if they get stuck halfway through because of a problem of remembering what they're doing. And so that's all that they know, the prompt. So rather than have, we might think of computer systems as, you log in and you give your password, and every now and again you apply updates to it and security patches and so on. It's really important to keep the interface, as far as the user is concerned, extremely simple. Yeah, similarly with that watch, they're given it by a nurse and they wear it for a week, and that's it. They don't have to do anything else. So I think that's part of the art of designing these sorts of applications, to make it as simple as possible. Go on, you were going to say? No, I thought you.
Me, I'm just like, these are people who started at the earliest points of anybody alive, and now it's almost like you're putting them into the future. So do they complete? They're not even reacting at all. Like this is weird, or like the kitchen's telling me to make a coffee now or something.
Yeah. So there are examples of that where where psychologically it can be a shock to them when the kitchen does talk to them. There's various solutions that are being adopted. For example, having somebody who they know prompt rather than just a remote voice like a sat nav to prompt can be one way to make it more reassuring. It'd be interesting to see as we get older, and we're more tech savvy, whether we're prepared to accept more technology when we get older. But there's a lot of there's a view that although we think we'll always keep up with technology, there's a view that once you actually get for a lot of people once they retire, then the technology that they're used to and familiar with effectively freezes, and technology moves on, but they don't keep up with it. So it may even be that even for people like yourselves, when in 30, 40 years' time, when you get to this point, that you may again, there may be some technology which is even a level above what you're used to, and the same problems will occur.
So that the government not giving us pensions anymore is effectively solving the problem.
Yes.
I had a serious question. You talked a lot about, let's say, the data flow and all of these aspects, but what are you going to do with the data in terms of extracting patterns? Could you specify whether there is a role, say, for machine learning in your side project, or what is happening already?
Yeah, no, there's quite a lot of machine learning in the side project, and Sebastian can answer any difficult questions in that area because he works on it at Dundee. So, for example, it happens at different levels. So, if you look at the accelerometry, then a lot of that's signal processing techniques. Yeah, and you can use machine learning in that, but a lot of it's about principal component analysis and so on. But in other areas, I think the area that I've been most impressed with so far has been with monitoring what people are doing in the kitchen based on, so they have accelerometers in utensils. So for example, in knives and spoons and forks, they go to John Lewis. Do you have John Lewis in Scotland? Yes. I'll be careful, it's not just an English company. So you go to John. I was worried you might have thought John Lewis was a man who I went to see. But so you go to a shop like John Lewis, you go to the kitchen department, you buy kitchen utensils, and then you cut the handles off them, and then using a 3D printer, you build new handles with a hole for an accelerometer in the middle of it. And then as people do things, for example with a knife, as they do, as they use it in recipes, then because of machine learning, you can tell the difference between chopping, slicing, dicing, coring, peeling, scraping, and all the different things that you do. And so I know Sebastian's doing some trials at the moment where he's videoing people in the kitchen making things like salads, and you mark up the video and then you capture the information, and you can use machine learning to try and match the two. So yes, machine learning is a key tool that's used in all of this.
But how do you go from these kind of low-level things like chopping, slicing, to actually inferring high-level information that you're interested in?
So that's the hard bit actually. So most of the work to date, which again actually is largely been done at Dundee, has been about using partial observable Markov decision processes, and trying to. So what you have to do is, if at any given time somebody's holding a knife and chopping, you have to work out, if they suddenly stop and you want to help them, you have to work out, well, what task were they doing and what the next stage is. Yeah. Now, one way to do it is to effectively get people to choose beforehand what they're doing. So in the kitchen, it can be through having them select a recipe in a simple way. And so the system has a good head start. But the process of having somebody go to the kitchen, just start to do something like pick up a spoon and a mug, and then you have to try and work out whether they're making a cup of coffee or a cup of tea and prompt them appropriately. That's a really hard task, and I think that'll keep even clever PhD students busy for quite a few years yet.
Time for maybe one more question. If not, let's thank Paul again. Small token of gratitude.
Well, it's very kind. Very traditional. Thank you.